Socotra is an island that shouldn't exist, and for good reason. Remote islands are supposed to be volcanic. They're meant to rise violently from the ocean floor. Fresh basalt, black rock, geological newborns like Hawaii or Iceland. If you see something sitting alone in deep ocean, the rule is simple. Magma made it. Socotra breaks that rule immediately. It isn't volcanic, it isn't young, and it isn't supposed to be sitting out there on its own. Socotra is a fragment of a continent. Ancient crust that once belonged to Africa and Arabia, stranded in the Arabian Sea like a piece of geological debris that drifted too far from home. And yet that's only the beginning of why it shouldn't exist. Because it didn't just break off and sit quietly. It was drowned, uplifted, tilted, faulted and partially submerged again, then lifted a second time, all while sea levels rose and fell by over 100 meters. By any normal geological logic, that kind of instability should erase biological identity. Instead, Socotra became one of the most biologically distinct islands on Earth. So how did this happen? To understand that, we have to go way back, long before the Gulf of Aden even existed. The foundation of Socotra is Neoproterozoic crystalline basement. That's a fancy way of saying its core rocks formed roughly 800 million years ago, during a time when early multicellular life was just beginning to experiment in the oceans. These rocks are granites, gabbros, amphibolites and schists, deep crustal rocks that originally formed 15 kilometers underground before later being pushed back up toward the surface. Granite, if you're picturing it, is the same coarse crystalline rock you see in kitchen countertops, but here it represents the frozen roots of an ancient mountain belt. For hundreds of millions of years, that crust sat on the eastern edge of supercontinents, first Gondwana, then the combined Africa-Arabia landmass. It was submerged under shallow tropical seas again and again, accumulating thick blankets of limestone. Limestone forms in warm, shallow marine water, often from coral reefs and shell debris. If you've seen the white cliffs on Socotra's plateaus, you're looking at that marine history. So before Socotra was an island, it was a submerged continental shelf. Then everything changed around 30 to 20 million years ago. The Arabian plate began to pull away from Africa. This process is called continental rifting, when a continent literally stretches and tears apart under tectonic forces. As the crust thins, it fractures along large faults, drops into basins, and eventually new oceanic crust forms between the separating plates. That's how the Gulf of Aden was born. Socotra sat right in the middle of that tearing. Instead of forming from volcanic magma rising through oceanic crust, Socotra was carried away as part of a rift shoulder, the uplifted edge of a continent being pulled apart. A rift shoulder is basically the elevated rim that forms alongside a spreading fracture zone. But here's where the story gets complicated. When rifting first began, Socotra didn't instantly become a lonely island. For a time, it was still connected to the Horn of Africa via what geologists call the Socotra Platform, a shallow extension of continental crust stretching towards Somalia. Then deeper structures came into play, the Guardafui Basin, a long, deep graben. A graben is a block of crust that drops down between two faults, essentially a tectonic trench. That basin deepened as rifting accelerated. Around 20 to 17 million years ago, true oceanic crust began forming in the Gulf of Aden. Once that happened, separation became permanent. Socotra was no longer just part of a stretched continent, it was marooned. But isolation didn't immediately produce today's dramatic landscape. In fact, parts of Socotra later subsided, meaning they dropped downward relative to sea level. Around 16 million years ago, shallow marine sediments were still being deposited in places. That tells us the island wasn't a towering mountain stronghold at that time. The dramatic relief we see today, especially the Haggier Mountains, appears to be younger. The Haggier Mountains are the jagged crystalline core of Socotra, rising to about 1,540 meters. Their final significant uplift likely occurred between 9 and 6 million years ago. That uplift was probably driven by renewed tectonic adjustments along the spreading ridge in the Gulf of Aden. Imagine pulling apart a thick piece of bread. The crust stretches, splits, and parts of it bulge upward while other parts collapse. Socotra's eastern block bulged. That late Miocene uplift is critical, because it means Socotra's modern mountainous backbone is relatively young in geological terms. It also means that limestone layers deposited in shallow seas are now sitting more than a kilometre above sea level, clear evidence of strong vertical movement. And while all of this was happening, global sea levels were swinging wildly. During the Pleistocene glacial periods, especially around 130,000 years ago, and again during the last ice age, sea levels dropped by up to 130 to 140 meters. That exposed much of the Socotra platform. But here's the key detail. Even at maximum sea level low stands, there was still over 70 kilometres of open water separating Socotra from Africa. Close enough for rafting events, too far for stable land bridges. That's evolutionary gold. Isolation with occasional colonisation is the perfect recipe for endemic species. You get genetic input, but not enough to homogenise the system. Now let's talk geology beyond tectonics. Socotra's lithology, meaning the types of rocks present, creates sharp ecological zoning. The Haggier crystalline rocks weather into mineral-rich but thin soils. The limestone plateaus create alkaline soils. High pH soils form from carbonate rock, which favour specialised drought-adapted plants. The island is arid. Coastal rainfall can be under 100mm per year, but the mountains intercept a fog, a process called orographic uplift, where moist air rises, cools and condenses. Fog drip provides additional moisture at elevation. That microclimate diversity, from hot coastal plains to foggy highlands, creates ecological niches in a relatively small area. Now about mineral wealth. Socotra has documented occurrences of granitic rocks, gabbros, metamorphic complexes, and some minor volcanic intrusions. There have been surveys noting potential for dimension stone, limited industrial minerals, and small-scale occurrences of metallic minerals associated with crystalline basement. However, it was never developed into a major mining province. Why? Because its economic isolation outweighs its geological potential. Any mineral deposits present are modest compared to mainland Africa or Arabia. Socotra's real value turned out not to be metallic, but biological. And that brings us to the flora. About 37% of its plant species are endemic, found nowhere else on Earth. The dragon's blood tree is often presented as the symbol of this uniqueness. It's a tertiary relict, meaning it represents a lineage that was once more widespread millions of years ago, but now only survives in isolated pockets. Socotra acted as a refugium. A refugium is an area that remains environmentally stable enough during climate shifts to preserve ancient species while they disappear elsewhere. But here's the twist that makes Socotra truly unique. It didn't remain stable. It was uplifted, partially submerged, and exposed to repeated climatic swings. And yet its isolation windows were always just enough. Never fully connected, never completely erased. It exists in a tectonic sweet spot, isolated enough to diverge, dynamic enough to reshape habitats, but never catastrophically reset. That's why it feels like it shouldn't exist. Most continental fragments either remain attached or fully integrate into new landmasses. Most islands either remain volcanic cones or erode into atolls. Most arid landscapes don't preserve ancient lineages. Socotra is a continental fragment in open ocean, a rift shoulder turned island, a carbonate platform lifted over a kilometre, a tectonic block tilted along transfer faults, fractures that accommodate sideways movement during rifting, a place where Precambrian granite meets Miocene reef limestone in the same skyline, and biologically it's a living fossil garden balanced on active plate tectonics. If anything, Socotra shouldn't have maintained continuity long enough to build such deep endemism. Its geological history reads like instability, its biological outcome reads like permanence. That contradiction is the real story. Socotra is an island that shouldn't exist, not because it's impossible, but because it defies the usual rules of island formation, tectonic stability, and evolutionary persistence. It's what happens when continental crust gets torn away, but not completely erased. It's what happens when isolation is imperfect. And it's proof that plate tectonics doesn't just build mountains, sometimes it builds worlds. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.